Hey guys, how you doing? I hope you had a great spring break. Want to get into some new content here, and we'll talk about this a little bit on during our video chat. So if you're watching this before the video chat, this is one of the things I want to talk to you guys all about is the updates to the AP exam and how that's going to affect sort of the end of our year. And so just very quickly, um, I did not want to do differential equations just yet. I wanted to sort of end with this, but that's okay. We can switch the two because differential equations is definitely apparently on the exam, or at least it's in the topics that they said would be included. So the last part, which we were going to do, which is solids of or finding solids using rotation of regions that are created by two or more functions. That was what we were going to go right into because it heavily involves using integrals, and we kind of just got done techniques of integration and accumulation and things of that sort. And so it was a nice transition into sort of the last application of integrals. Differential equations does use integration, so it won't be too far off, but it kind of more uses a mixture of both derivatives and integrals. And so this is kind of where I like to end off the year typically, but we're gonna jump right into it so we can cover it in order to definitely satisfy everything for the AP exam. Okay, so what I'm going to do is kind of just start off explaining what is a differential equation. Why do they have sort of a special name? And in fact, this is a really important branch of mathematics. If you were to study math past high school, they have entire courses dedicated to differential equations and everything that you can do with them and how you can work with them. So I'm going to give you sort of a brief introduction to it. We're really just going to be working with differential equations on a foundational level. So everything that we do would definitely be covered in sort of an introductory to differential equations class. And then it would go a little bit further than what we'll do, but this is sort of the beginning, definitely. And so essentially, it's going to look really familiar to you because it's really just a derivative, right? I mean, it's an equation that tells you the instantaneous rate of change. The biggest difference between a lot of the derivatives we've worked with and differential equations that we'll work with is that most likely there's going to be x's and y's mixed within the derivative itself. Okay, I have down there think implicit differentiation because this is sort of the closest thing that you had done similar to differential equation where in the end, there might be both y's and x's mixed into a function or into a derivative. And so that's similar to what we'll do. We're not going to be doing implicit differentiation today. That idea will come back into play during this unit, but specifically today, we're not going to be looking at that. I just have a couple of examples of what differential equations might look like. All right, and so I tried to show you just sort of a variety. It certainly could just be made up of only x's or only y's. But again, typically what we'll be doing is having a mixture of both x's and y's. Okay, so these are all examples of differential equations. Yes, they look just like derivatives, right? dy dx is the derivative. And so I don't want you to get sort of freaked out by the fact that they're called differential equations. Why do they have a different name? And again, it's just a differentiation of the study of differential equations as opposed to it's a derivative, so on and so forth. Okay, so here are a couple examples of differential equations. Biggest difference between evaluating a differential equation and evaluating a derivative that we know is we need both an x and a y coordinate. Right. So if I wanted to find the instantaneous rate of change, the slope of the tangent line for the function that I might be working with, I need both the x and the y coordinate of that point in order to get that instantaneous rate of change. Okay. So that's sort of the key differences between what we've done and what we're going to be looking at. Okay. So here is the big idea with differential equations, though. Okay. So eventually we're going to get to this point where we are going to be finding functions that, quote, fit the differential equation. So I'm going to explain what that means in just a minute. Everything that we do starting today, moving forward, are going to be versions of finding functions that, quote, fit the differential equation. We're going to start small today. So we're not going to do a whole lot with actually solving differential equations, which I'm about to kind of show you. But this is probably the most important piece of the unit itself, is finding functions that relate or that actually you can solve for using this differential equation. So here's a quick example. Maybe this will clear up some of the confusion, because I know some of this is definitely difficult to understand just right off the bat. I'm given a differential equation, dy dx equals 2x divided by e to the y. Okay. What I want to find is some function in the form of y equals with all x's on the right-hand side. Okay, so I don't want any y's other than the y equals part. And that function's derivative needs to match this differential equation, meaning that they are exactly equal to one another. Okay, so what function's derivative is equal to 2x over e to the y? Hard part here is, right, because you've heard that before. Basically, I'm asking you, like, what's the integral of 2x over e to the y? And so the hard part here is that, well, we don't know how to integrate a function with two variables, right? We only know how to integrate a function in terms of x. As soon as that y is thrown in there, we have to work with it a bit differently, okay? We won't be solving in that way today. We will eventually. That's like the big goal. But here's what I mean by a function that fits this differential equation, or a solved function for this differential equation. So the answer is the natural log of x squared. Okay, so again, I'm not going to show you just yet how we got that answer. Okay, but this top piece up here, this is the actual answer. All right, but I want to show you just what I mean by solving a differential equation and how it can be useful. So we've got, this is the answer, natural log of x squared. I can take that derivative, right? Because there's only, well, I could take a derivative even if there was y's here with implicit differentiation. But even easier, I can take this derivative just by using the chain rule, right? So I know the derivative of the natural log is 1 divided by the inside, so 1 over x squared. Chain rule says multiply by the derivative of the inside. So that would be 2x. That comes from x squared. So 2x divided by x squared simplifies to 2 over x. So now you might be thinking, well, you had said that the derivative, the differential equation, isn't 2 over x, it's 2x over e to the y. So how is 2 over x exactly the same as 2x over e to the y? Well, y prime, which is the same thing as dy dx, right? So here's y prime, derivative. We did say is equal to 2x over e to the y. What if you were to replace your y equals equation into this derivative for y itself? So I know what y equals. Y equals the natural log of x squared. So what happens when I replace y with the natural log of x squared? 2x over e to the y equals 2x over e to the natural log of x squared. Well, if you know some exponential and logistic properties, e and the natural log are inverses of one another. Those two things cancel each other out, so they go bye-bye, right? And I'm just left with 2x over x squared, which simplifies to 2 over x. So they're exactly the same. So again, the emphasis here is, what is a differential equation and how can we work with it? How can we solve a differential equation? Well, we're trying to figure out, based on some derivative that we are given, and most of the times it has x's and y's within that derivative, what function in terms of y equals, in terms of x, gives me the exact same derivative as what I started with. Okay, and so there's the idea there. 2x over e to the y, replace y with the natural log of x squared, you get the exact derivative from the natural log of x squared itself. Okay. All right. Let's move on to, I want to get into one more slide just about differential equations. And this is just in case you read about this or see this and talk about it a little bit. Something called a first order differential equation. We are only going to be working with first order differential equations. And all that means is that we're going to be working differential equations that only have a first derivative on either side of the equation. Okay. For example, there could be a second or third order differential equation, so on and so forth. A second order differential equation would have a second derivative mixed in, meaning y double prime equals y prime plus xy to the fourth. That's just an example. We will not be working with that. It's much, much more difficult to solve that differential equation than it is to solve the differential equations we're going to be working with. Basically, you'd have to find some function whose second derivative is equal to its first derivative plus x times the function itself all to the fourth power. Really difficult to do. And so we're not going to be getting into that. If you were to study differential equations further, you might get into something of this sort. But we're only going to be working with first order differential equations, similar to the example I just showed you, where there's only a first derivative, y prime equals dy dx equals, and then just x's and y's, no extra derivatives. Okay. We're going to be working with differential equations in a couple of different ways. Today, we are only going to be focusing on working with them graphically, okay? Eventually, we'll work with them analytically, meaning we'll be able to solve differential equations analytically using integration to find that y equals equation. Today, however, I want to talk about the graphical approach, okay? Because if you think about it, if a differential equation is a derivative, and I can plug any xy coordinate into that differential equation, giving me the slope of the tangent line at that point. Well, if I were to plug in, let's just say, just imagine you could do this, plug in every single xy coordinate into the derivative, into the differential equation, and draw a little mini slope line at that xy coordinate that corresponds to the differential equation you were given. Well, if you find the slope at every single point on a function and draw just a little tiny line that represents that slope, and then you connected all of those slopes together, you would have the function itself. So in other words, if I were to look at the function x cubed, right, I know that if I start from the left, right, that the slopes of x cubed are pretty vertical, like pretty close to vertical, right? So further down the negative x-axis and further down the negative y-axis, the slopes might look like that, right? But then they start to get a little less steep and a little less steep and a little less steep. Eventually, they actually start to zero off right around the origin, and then they start to get a little more steep, right? And so imagine you are calculating the individual slopes at every xy coordinate. So here's an xy coordinate, here's an xy point, here's an xy point, so on and so forth. And you were just marking those xy points with little tiny line slopes, okay? Eventually, you would have enough where you wouldn't even see a gap. You wouldn't even see a difference. You would actually be able to draw what's called a smooth curve. Oops, sorry, I got away from it a little bit there, right? I'd be able to draw with a smooth curve that connects all of those slope lines and creates an actual function. And so that's how we're going to be looking at differential equations today. We're going to use differential equations to graph tiny slope lines on a coordinate plane. And when I graph those tiny slope lines, I may see a function that I recognize. And if I'm able to recognize that function, then essentially you've solved the differential equation because you know what function's derivative you're working with. And so if you know what function's derivative you're working with, then that's technically solving the differential equation. Okay? So what we're going to be working with is something called a slope field. Why is it called that? Again, we're analyzing the individual slopes at all points on a function. So what we're going to be doing is actually graphing and analyzing the instantaneous slopes. So we're actually going to be creating slope fields from differential equations. We'll have to match given slope fields to functions and differential equations. So we might not be given either the function or the differential equation, just a picture of the slope field. And we have to match it to either a function or a differential equation itself. And then again, we actually will create a slope field. This is what we're going to be doing today. Okay, so we're only going to work with slope fields today. Okay, let's move on. So let's jump into an example. Okay, I gave you kind of a rough example there with at the x cubed graph. This is a much nicer version of what I just tried to do. Okay, so this is the differential equation dy dx equals 2x. Pretty simple differential equation. It's not even a y there, right? Again, what would the goal be here? We'll figure out what function's derivative is equal to 2x. So what function's instantaneous slopes could I find by using the function 2x? And hopefully you recognize that. It's pretty easy, right? It is a parabola, x squared plus some value c. All right, I have a little reminder here that plus c represents a family of functions. So x squared plus 0, or just x squared itself, is the parabola that's at the origin. If I add 1 to it, I move that parabola up 1. If I subtract 2 from it, I move that parabola down 2, right? So that plus c can mean any value, and all it does is move the parabola up and down the y-axis. So this is what a slope field for dy dx equals 2x looks like. You can see that all these little lines here, all these little line segments, they actually represent the instantaneous rate of change for every function x squared plus c. Right? Now, it's pretty impossible to do it for every single xy coordinate, meaning every number in between 0 and 1 and every number in between 1 and 2, so on and so forth, because if you did that, it would just be a black screen here, right? So typically you only do it for either large values or even values of x and y, so just 1, 2, 3, negative 1, 2, 3, or maybe even 1/2, 1, 3/2, 2, 5/2, so on and so forth, just to give you a picture, just give you an idea of what those slopes might look like and what functions might match this differential equation. Okay, whoops, sorry. So here's a good animation, I think, right? If I were to take this parabola and actually superimpose it onto the slope field itself, do you see how the slope lines, right, these little line segments, actually match the parabola itself? They actually start to form the parabola. And so one of the things that you might be tasked to do is actually sketch a solution using a slope field. So if I were to just give you, let me take this out of the way for just a second, this slope field and nothing else, and say sketch a solution that goes through the point 0, 0. Well, a solution that goes through the point 0, 0 would just be x squared itself, right? No plus c there at that point. And so I could start at 0 and actually start to follow these slope lines. Okay, it might not be perfect, but I should get an idea. That last one's bad. The second one's really bad. I should get an idea of what a solution to the differential equation might look like, right? Just by following the slope lines itself. And so I could actually sketch my own solution to the differential equation just by using the slope field. Okay, so and that's the graphical sense. Now, that method of solving a differential equation is really nice when you can tell what function you just sketched, right? So we know what a parabola looks like. We know that this answer is going to be some form of x squared plus c. There are differential equations that don't look this nice. We may not know what the function we just sketched is or represents or it comes close to. Okay, which is why we have other ways of solving for differential equations, which we'll get to eventually. Okay, but this is just, again, another example of what a slope field looks like, how you can use it, and how we might use it. All right, so again, plug in any xy coordinate into this differential equation, and you get the slope that's represented. Quick example, let's try and pick one out here. Well, first off, notice that along the y-axis, all x values are equal to 0. So every time you plug in anything on the y-axis, so 0, 1, 0, 2, 0, 3, the slope is 0. So there's a little 0 slope there. Okay, it's a horizontal line. If you were to move to something like 1, 0, well, at 1, 0, which is pretty close to this point right here, this little slope line, the slope should be 2 times your x value, which is 1 or 2. So your slope should be 2. If you were to look at this little line segment that I've circled, that line has a slope of 2, right? Rise over run. And so you would just go along every single xy coordinate, figure out the individual slope, and just draw a little line segment that has that slope, and it starts to create this slope field. Okay, let's move on to another example. So I've covered up the answers to this one. So what I want you to do is, in just a minute, pause the video and try and figure out what function this slope field might represent. Okay, so what function do you see coming out of this slope field? And furthermore, what is a differential equation that might match this slope field? So what slopes can you get by plugging in xy coordinates into the differential equation? Go ahead, give it a try. Okay, so hopefully you're able to see it. It's definitely one of the more popular functions we use, right? You can start to see this sort of wavy effect that comes out of this slope field. And so the function itself is sine x, okay, plus c. So you can start, hopefully you see it a little bit where we've got, if we start at the origin, right, we go up to 1, we can actually start to follow this differential equation really nicely, right? And so you start to see the sine curve come out of it, and we could go the opposite way as well. All right. And so all I did was follow there. And that's another example of sketching a solution curve through a certain point. So that is the function itself. Okay. Another thing you might have to pick out is, well, right, what differential equation is represented by this slope field? And so since we know the function itself, we could just take its derivative, and hopefully we all know that that is cosine. But maybe we didn't start with this at all. Maybe this was the only thing we were trying to find, is what differential equation is represented by this slope field, and it is cosine itself. And again, if you want to try to test that out, or maybe just a further understanding of what I mean by this, the cosine is the differential equation that matches this slope field, pick some value within this graph, right? So pick any value of x and plug it into cosine and see if that little line segment matches the value that you plugged in. So let's just do maybe 2 of them here, right? So let's do, let's just do cosine of 0, right? Because that one's easy for us. I know the cosine of 0 is positive 1. And so this little slope right here, this little line segment that I circled, has a slope of 1. All right. What if we tried... Let's try something like, let's look at like pi, right? So pi is approximately 3.14, right? So approximately 3, which is pretty close to this value right here. Okay. Notice that the cosine of pi, which unit circle tells me is -1. This little line segment has a slope that's pretty close to -1, if not exactly -1. All right. So right there, that suggests that cosine does match up. All right. Okay. Let's move forward a little bit here. So now I want you to think about it this way, because here's a slope field, and a lot of the times this is a more common question that you'll receive. We're going to be given slope fields that we don't immediately recognize, or maybe never recognize, what function we're actually working with. All right. So the first 2 examples, hopefully you at least saw the x squared come out when I sketched it, and hopefully you saw sine of x come out when I sketched it, and maybe you saw that right away. For this particular example, we might not know exactly what the function is we're working with, but we can still pick out a differential equation when given some options. All right. And all we have to do is just analyze what's happening with this particular differential equation and this particular slope field at certain points, and see if they match the differential equations that we're given, and what values can we work with, which are easier to work with and which are not. Okay. So again, I'm going to encourage you right now, try and pause the video and try and figure out which one of these differential equations is represented by this slope field, and why? There are a couple of key characteristics of this slope field that you're seeing in front of you that match only one of the differential equations listed to the left. Give it a shot, and then the next slide I'll explain the answer. Okay, let's take a look. So the answer is B. All right, it's dy dx equals x minus y. Hopefully you had some success with that. Let's talk about why it's B. So there are a couple of key characteristics that I see within the slope field itself. The first one, the one that stands out the most, and this is typically something you want to look out for, are any slopes that are equal to 0. So any horizontal line segments that you see. And there's actually like this step piece, this step function almost comes out of it right in the middle there, where I noticed that at every xy value where x is equal to y, the slope is 0. Right? So at 1, 1, the slope is 0. At 2, 2, slope is 0. At -3, -3, the slope is 0. Meaning that if I were to subtract those two values from one another, I should get 0, right? X minus y, if x equals y, that should be 0. That was my first clue that the answer was B. Okay. My second clue might be this piece right here, right? So notice this straight line, all right? What I notice is that those line segments are straight through this entire piece where x is exactly 1 greater than y every single time. X is equal to 0, y is equal to -1. X is equal to 1, y is equal to 0. X is equal to 2, y is equal to 1, so on and so forth. And so if that's true, then if I subtract x from y, I should get 1, right? So dy dx equals 1. 2 minus 1 is 1. 1 minus 0 is 1. 0 minus -1 is +1. And it looks like these lines do have a slope of 1. And so putting those two pieces together and looking at my other options, B was the only valid choice. Because if I chose x plus y, then at 1, 1, the slope wouldn't be 0. It would be 2. That doesn't make sense. At dy dx equals x divided by y. Okay, well, at 1, 1, the slope would be, again, 1. So that's gone, right? Dy dx equals x times y. Again, at 1, 1, that slope should be 1, not 0. So that one's gone. And so you can definitely use elimination, but some of them, it is a lot easier and a lot quicker if you just recognize those really key characteristics and then just work off of that. Okay, so we're actually almost done. This is hopefully not too long of a video. And this is the last thing that I'm going to do with you. And this is sort of the last piece that we'll have to do with slope fields itself, which is actually creating or constructing a slope field. And so this is from an actual past exam 2016. It's a very good chance that you will have to do this on the AP exam, even with the changes to it. And this is actually one of those home run problems because once you see and do one or two of these, it's really simple. Okay. All we're doing is creating or constructing a slope field based off of some given XY coordinates. All right. And so you will always be given a differential equation. And then you'll also be told what XY points to create those little line segments. All right. So really what we're doing is a really simplified version of something that looks like this. We're going to be creating these line segments, but only for like max 6 or maybe like 8 points at total, right? So this one is only 6 points, and it's really pretty simple. So all we have to do is just sketch the slope field. All you're going to do is go through every individual point that you're given. So there's 6 of them. So 0, 2, 0, 1, 0, 0, 2, 2, 2, 1, and 2, 0. For each one of those individually, you're going to be plugging the XY coordinate into this differential equation. So for 0, 2, this first one up here, so for 0, 2, if we were to plug in that XY pair into this differential equation, what would happen? Well, y is equal to 2, so that would be 2 squared, right? Divided by x is equal to 0, 0 minus 1, which is 4 over 1. 4 over -1, which is equal to -4. So I would, at this xy coordinate, draw a line segment that is close to -4. Obviously, we're not going to be exact, but we want to be close to it. So what does -4 look like as a slope? Maybe something like that. It should be a straight line, right? So it's a straight line segment. You would go ahead and do this exact same thing for every single point that is listed, and it's just the remaining 5. Once you do that, you've created a very small slope field for this differential equation. All right. Do this. Pause the video and give the other 5 a shot. All right. And then I'll reveal and explain the answer. Okay. So here is the answer. Hopefully you got something that looks similar to this. And also what I did was just write out the individual slopes for each pair and show you that they match up definitely. Okay. So we already did 0, 2. You can see that that was -4. That's this one right here. That one looks a lot nicer than the one I drew. And then at 0, 1, we had -1. And so we drew a slope that is negative, right? But it's definitely not as steep as -4. All right, so one of the key points or one of the key ways to get these problems correct is that your slope lines are clearly different if they are different values. I know that sounds weird because they obviously should be, but it's really easy to draw like a -1 slope that looks exactly the same as -2. We don't want to do that. We want to make sure that if I have a slope of -1 and then a slope of -4, that these lines do look different. Don't get lazy and don't get sloppy. It's a really easy question, right? Make sure that this is definitely different than this one because they are different slopes. And then at 0, 0, plug in 0, we get 0 itself. So it should just be a little small. You can't really, it's bolded here. A little small horizontal line segment. And then the same thing for these 3 right here, right? So at 2, 0, 0 again, 2, 1, we see the slope of 1. It looks exactly like the -1 slope, just mirror imaged, right? And then same thing for 2, 2. It looks exactly like -4, just a mirror image. And that would be a complete slope field. Okay. So that's it for today. I just want to introduce you to differential equations, introduce you to slope fields. Here is what we will be doing eventually. So we're going to use differential equations to approximate values of functions. So if I'm given a differential equation, could I come up with the slope of a tangent line that might give me an output? So that would be in the case that we can't solve the differential equation. We just want to be able to use a differential equation to approximate other outputs. We're going to talk about increasing, decreasing, concavity. Obviously, if we're working derivatives, that opens up that whole world. We're going to be doing some real world modeling, specifically in the realm of exponential growth and decay, and sort of a really popular differential equation within that. And then finally, the last thing is the big part, which is we're going to be solving differential equations. And that's where our integration practice and our integration techniques are really going to come into play. All right. Homework will be on my Malvern. I hope you guys have a great day. Please let me know if you have questions. I know this stuff is new and it can be a little bit confusing in the upfront. I do have extra resources on my Malvern if they're helpful. Okay. All right. Have a great day. I'll talk to you soon.